Okay, I'm starting then. All right, so just okay. Okay. All right. So what did we get? So let's come back here. So this hypothesis 2 gave us that the comparison angle between xy at P is less than or equal to the angle between x bar double prime, r bar double prime at P bar double prime. And here x bar double prime, r bar double prime, this distance is less than or equal to the distance x bar r bar here. So therefore the angle at P bar double prime between x bar double prime, r bar double prime, this is less than or equal to the angle at P bar between x bar and r bar, right? Is this clear? Yes?
Yes, sir.
And this angle is the same as the angle at P bar between Q bar and R bar. And that is the same as the comparison angle at P between Q and R. So you put these inequalities together, you get that the angle, comparison angle between XY at P is less than or equal to angle P bar double prime, X bar double prime, R bar double prime, which is less than or equal to the comparison angle between QR at P, right? So therefore, we're done. Okay. Is this all right?
Yes.
Okay, so that proves the equivalence of these three statements. So we're done. Okay. All right, any questions? Is this okay? Okay. So let's move on. So we have this equivalent characterization of cat kappa spaces. Okay, so now we come to a useful lemma called Alexandrov's lemma. So it says the following. So suppose we are given two triangles in M2 kappa which share a common vertex. Okay, AC. The triangles are ABC and AB prime C, such that B and B prime, they lie on opposite sides of the line passing through AC of this geodesic. Okay. Then let's call the angles like this. So the angle at B is beta, at B prime is beta prime. The angles at A are alpha and alpha prime, and the angles at C are gamma and gamma prime. And let's call these side lengths C and C prime. And this one is A and A prime. And this common side, let's call it B. Okay. Now let's suppose that the sum of these two angles, gamma and gamma prime, is greater than or equal to pi, like in this picture. Okay. This gamma plus gamma prime is greater than or equal to pi. Then we can say, first of all, that A plus A prime, this side plus this side, is less than or equal to C plus C prime. Okay. Secondly, we can do the following. So suppose we construct one triangle in M2 kappa by straightening out this side. So what do I mean? That means I construct a triangle whose sides at the vertex A bar are C and C prime, the same as these sides. Okay. But the third side is equal to the sum of these two sides, A plus A prime. Okay. So this side is A and this is A prime. All right. So I've sort of straightened out this, okay? Is it clear what this new triangle is? A bar, B bar, B bar prime. Yes, it has sides C, C prime and A plus A prime, okay? So then I get a point corresponding to C also, C bar here. Yeah, and I have a distance here, B bar. And I get a new angle at A bar, which is alpha bar, okay? And I get new angles here, which are beta bar and beta bar prime, okay? So what should you expect if you sort of straighten this out? First of all, this side should get longer, right? And these angles should get bigger, right? This beta should get bigger, beta prime should get bigger, and this angle at A should get bigger, right? So these are what you expect, okay? So in fact, that's what happens. So we get that alpha bar is greater than or equal to alpha plus alpha prime. Beta bar is greater than or equal to beta. Beta bar prime is greater than or equal to beta prime. And this new length, B bar, is greater than or equal to B. Okay. So this is Alexandrov's lemma. And any one equality here holds if and only if all of the equalities hold. And that holds if and only if gamma plus gamma prime is equal to pi. Okay. So is the statement clear?
Yes, sir.
Okay. So let's do the proof. So the proof is just this very simple construction. What you do is you take the line from B to C and you extend it further. Okay. So that it has length A prime, which is the same as this A prime here. All right. So now this angle becomes 180 degrees. It becomes pi here. And so I get a new point B double prime. Okay. And I get a new side here, C double prime. Okay. Now I get a new angle here, gamma double prime. This angle is still gamma, right? But I have this gamma double prime here. So now what happens? Gamma plus gamma double prime is equal to pi. And this is less than or equal to gamma plus gamma prime, right? I'm given that gamma plus gamma prime is greater than or equal to pi. So I can cancel gamma from both sides. What I get is that gamma double prime is less than or equal to gamma prime. Right? That I can see, of course, in this picture. Gamma double prime is less than or equal to gamma prime, right? But now, if I compare these two triangles, ACB prime, so here the sides are at the vertex C are B and A prime. And if I compare this triangle, ACB double prime, then again the sides at the vertex C are B and A prime. So again, these have the same sides at the vertex. Therefore, if this angle is smaller than this angle, then this side is less than or equal to this side, right? So that means that C double prime is less than or equal to C prime. Yes? Is that clear? Right? If the angles are smaller, then the opposite sides have to be smaller, right?
Yes, sir.
Okay. So C double prime is less than or equal to C prime. Now I look at A plus A prime. That is equal to this distance, right? From B to B double prime. By the triangle inequality, this A plus A prime, this is less than or equal to C plus this C double prime, right? Okay.
Yes.
So A plus A prime is less than or equal to C plus C double prime. And C double prime is less than or equal to C prime. So that becomes less than or equal to C plus C prime. Okay, so we've proved the first inequality. We've proved part one, that A plus A prime is less than or equal to C plus C prime. Is this okay? Yeah, this is part one. We've proved this. All right.
Yes, sir.
Okay. Now we have to look at the other inequalities. Okay. All right. So let's look at this picture. So it's just a matter of comparing triangles. So let's look at the triangle ABB double prime. So A, B, and B double prime, and A bar, B bar, B bar prime. Okay. So let me show you again. A bar, B bar, B bar prime. Okay. So now these triangles, they have the same sides at the vertex B and B bar, right? This has length C and A plus A prime, and this has length C and A plus A prime, right? But now the opposite side here, C double prime, we showed is less than or equal to C prime, right? Yes. Therefore,
Yes, sir.
this angle here, which is beta, is less than or equal to this angle here, which is beta bar,
Yes.
right?
Yes. Right.
Okay. So that proves that beta is less than or equal to beta bar. And then a similar argument interchanging B and B prime will show you that beta prime is less than or equal to beta bar prime, right? Is that okay?
Yes, sir.
It's just
Yes.
by symmetry. You just interchange B and beta prime, B and B prime. Okay. Now you compare the angles, the triangles ABB prime and A bar, B bar, B bar prime, the big triangle. So what is ABB prime? So it's A, B, B prime. Okay. So
We are joining B and B prime, right?
yeah, we're joining B and B prime. We're joining B and B prime. So let's look at these. So these have the same sides at. These have the same sides at A. Right. This has sides C and C prime, and this other triangle A bar, B bar, B bar prime. This also has sides C and C prime. But now the opposite side, in this triangle, it's A plus A prime. And in this triangle, B prime is less than or equal to A plus A prime by the triangle inequality, right?
Yes.
Mod of B prime is less than or equal to A plus A prime. That tells you that this angle here will be less than or equal to this angle here, right? Alpha bar. Is this clear? So therefore, we get that alpha plus alpha prime is less than or equal to alpha bar. Is this clear?
Yes, sir.
Okay. And finally, we need to show that B is less than or equal to B bar. So for that, we look at the triangles ABC and A bar, B bar, C bar. So at the vertex B, these have the same sides, C and A, right? It's C and A over here. And over here also it's C and A. But I know that this angle beta here is less than or equal to this angle beta bar, right? That we already showed. Therefore, this side B is less than or equal to this side B bar. Is this clear? Yes?
Yes, sir. Yes.
Okay, so therefore B is less than or equal to B bar. Okay, so finally note that what happens in the case of equality. So all of these inequalities, when they're equalities, they're all equivalent to each other. So to see that, note that if gamma plus gamma prime is equal to pi, this is if and only if gamma double prime is equal to gamma prime, right? Here's gamma double prime and here's gamma prime, right?
Yes. Yes.
So this is if and only if gamma double prime is equal to gamma prime. And this we saw is if and only if C double prime is equal to C prime, right? This is C double prime and this is C prime, right?
Yes. Yes.
Okay. Now, C double prime and C prime, these are the opposite sides we used when when looking at the angle beta and beta bar, right? C double prime is equal to C prime. This is if and only if beta is equal to beta bar, right?
Yes, sir.
Okay, because that we got by looking at A, B, B prime and A
Mhm.
bar, B bar prime. So those had the same sides at the vertex B and B bar, and the opposite sides were C double prime and C prime, right?
Mhm. Yes.
So C double prime is equal to C prime if and only if beta is equal to beta bar, and beta equal to beta bar, that's if and only if B is equal to B bar, right? Right, because that was how we got B less than or equal to B bar from beta less than or equal to beta bar, right? So again here, equality holds if and only if B is equal to B bar. Is this clear?
Yes, sir. Yes.
Yeah, so all of these equalities are equivalent to each other. And finally, gamma plus gamma prime equal to pi. This holds if and only if this length B prime is equal to A plus A prime. And that equality is equivalent to alpha plus alpha prime equal to alpha bar, right? Right, because remember we used B prime less than or equal to A plus A prime to show that alpha plus alpha prime is less than or equal to alpha bar, right? So equality here will imply equality here. It will be equivalent to equality here. Is this clear?
Yes, sir. This
Okay,
is
and
fine.
finally, similarly, beta prime is equal to beta bar prime if and only if B is equal to B bar. Okay,
Mhm.
all right. Okay, so
Yes.
that proves Alexandrov's lemma. Is this okay? Yeah, so it's just a matter of constructing this triangle here, this point B double prime, and then you just compare triangles with equal sides at a vertex. All right, and look at opposite sides. That's all. It's very simple. Is this okay? Yes. Yes, anyone? Hello, are you there?
Yes,
Is
that's
this
fine.
this is fine? Yeah. Okay. Okay. So now we can give a sufficient condition for a space to be cat kappa, a geodesic space to be cat kappa. So that is the following proposition, that if X is a length space and A is an angle function, it may be the Alexandrov angle, or it could be just some abstract angle function. So for a Riemannian manifold, it could be the Riemannian angle. Okay. Then first of all, the following are equivalent. One, if I take any geodesic triangle PQR, then the angle function between PQ and PR is less than or equal to the comparison angle. Okay. And two, for any geodesic triangle PQR, if P hat, Q hat, R hat is a triangle in M2 kappa with distance PQ equal to distance P hat, Q hat, and distance PR equal to distance P hat, Q hat. And if the angle at P hat is between Q hat and R hat is equal to the angle function PQ and PR, then the distance P hat, Q hat is less than or equal to the distance PQ. Okay. So let me just draw you a picture. So here's PQR. And I have the comparison triangle, P bar, Q bar, R bar. this angle is theta, which is the comparison angle. Angle P kappa QR. Okay, this is delta bar in M2 kappa. And I'm drawing another triangle. In M2 kappa, P hat, Q hat, R hat, such that, so this distance PQ is the same as P bar Q bar is, sorry, and PR is the same as P bar R bar, and P bar Q, this PQ is the same as P hat Q hat, and PR is the same as P hat R hat. Only in this triangle, the angle here is A, which is the angle function. Okay, so A is equal to A PQ PR. All right. This is my delta hat in M2 kappa. Okay. So condition 1 is basically one is that the angle function A here is less than or equal to the comparison angle, right? Is less than or equal to theta. Okay. Now this is equivalent to, so let me just write, 1 is equal to this statement, and this is equivalent to, so these are again two triangles which have the same sides at this corresponding vertex, P bar and P hat, right? This side is equal to this side, and this side is equal to this side. So therefore, this angle A is less than or equal to theta, if and only if the opposite side is less than or equal to the opposite side. So if and only if Q hat R hat is less than or equal to Q bar R bar, and Q bar R bar is the same as distance QR, right? And this is condition 2. This is condition 2, right? Oh, I've written this wrong here. It's not P hat Q hat. It should be Q hat R hat. So this is a typo. I'm sorry. It's a Q hat R hat should be less than or equal to QR. Okay. Sorry, this is a mistake here. This is a mistake. It should be Q hat R hat less than or equal to QR. Okay. That is condition 2. So 1 is equivalent to 2. Is this clear? Yes.
Yes.
Okay, this angle here, A is less than or equal to theta, if and only if this distance Q hat R hat is less than or equal to this distance Q bar R bar, which is the same as the distance QR. Okay. So 1 is equivalent to 2. Okay. Now, the proposition states also that either statement above implies that X is cat kappa. Okay. Either statement implies that X is cat kappa. So we'll show that 1 implies that X is cat kappa. That is, the angle functions are less than or equal to, I have an angle function which is less than or equal to the comparison angle. Okay. All right. So for example, if I had a Riemannian manifold where the angle function is always less than or the Riemannian angle is always less than or equal to the comparison angle, then my manifold would be cat kappa. Okay. All right. So that's what we're going to use to prove a later theorem. Okay. That so if the Riemannian angle is less than or equal to the comparison angle, then the manifold will be cat kappa. Okay. So, all right. So, okay. So I've written out the proof. Let me just draw you the proof. So one implies that X is cat kappa. So what I'm going to do is the following. I take PQR and I take a point X on the side QR. Okay. And then I draw this comparison triangle. P bar, Q bar, R bar. And I have the comparison point X bar, right? And then I have this distance here, and I have this distance here. So it's enough to show by what we proved in the previous proposition that the distance Px is less than or equal to the distance P bar X bar, right? Yes? Okay. Right?
Yes.
Okay. So now what I do is the following. I look at these triangles, PQX and PRX. So I form two comparison triangles for them. P tilde Q tilde X tilde, and I take another comparison triangle P tilde X tilde R tilde, and I join these two triangles together so that they lie on opposite sides of the line P tilde X tilde. All right. Is this clear? Okay, so basically this is delta bar is a comparison triangle for PQR. And then this is, let's say, delta tilde, and this is delta tilde prime. And delta tilde is a comparison triangle for PQX. And delta tilde prime is a comparison triangle for PRX. Okay. Is it clear? I'm not writing more. Is it all right? Yes. Okay.
Yes.
So let's look at these angles here, gamma and gamma prime. I want to use Alexandrov's lemma, right? So if this side is A and this side is A prime, and let me call this this length is B, then this length here is B also, and this is A and this is A prime, right? Because these are comparison triangles for these two triangles. And this let me call B bar, right? And then this side is also, this side is A, and this is A prime. So this is A plus A prime, right? Okay. And now what do I have? I have that gamma is equal to, so gamma plus gamma double plus gamma prime. So what is gamma? Gamma is equal to the comparison angle at P, sorry, at X is equal to the comparison angle at X between Q and P. And gamma prime is equal to the comparison angle at X between R and P, or P and R. Okay. Now what am I given? I'm given that comparison angles are bigger than the angle function, right? So this is bigger than or equal to the angle between XQ, XP plus the angle function of XP, XR, right? Yes? But now the angle function satisfies the triangle inequality, right? So this is greater than or equal to the angle function of XQ and XR, right? Yes, but XQ and XR, these are the forward and backward geodesics corresponding to a geodesic passing through X, right? So we know for those, the angle between C plus and C minus is pi, right? Yes? That's in the definition of angle function. The angle between C plus and C minus. This is the angle between C plus and C minus. This is equal to pi, right?
Yes.
Yeah. So therefore, the sum of gamma and gamma prime is greater than or equal to pi. Therefore, by the Alexandrov lemma, B is less than or equal to B bar, right? Is this clear? That's what the Alexandrov lemma says. B is less than or equal to B bar. But that gives us what we want, right? Because B is equal to the distance from P to X, and B bar is equal to the distance from P bar to X bar, right? So that's it. So therefore, the distance Px is less than or equal to distance P bar X bar. Is this clear?
Yes, sir.
Okay, so X is cat kappa by the previous proposition. Right, there we saw that you just have to check the cat kappa inequality for vertices and points on sides opposite the vertices, right?
Yes.
Okay, so that's it. Okay. So why are we interested in all this? Because we want to apply this to Riemannian manifolds. So let me state Alexandrov's theorem. Although I'm not sure, it might also be due to Topogonov. I'm not exactly sure, but I think this is Alexandrov's theorem. Okay, so the theorem is the following. Let X be a complete simply connected Riemannian manifold such that all sectional curvatures satisfy the sectional curvature I'll call K, well, Kp sigma. Okay, fine. This is less than or equal to kappa, right? For some, for all P in X and sigma 2 plane in TPX. Okay, and this is for some kappa less than or equal to 0. Then X is a cat kappa space. Okay. So if you like, in a sense, I mean, cat kappa is a way of saying that curvature is bounded above, sectional curvature is bounded above by kappa. That's really what cat kappa means. It's a metric way of saying that, okay? So, in fact, I mean, X is cat kappa if and only if all sectional curvatures are less than or equal to kappa. This is if and only if, actually, okay? So if X is complete and simply connected, then if the sectional curvatures are less than or equal to kappa, then X is cat kappa. And conversely, if X is cat kappa, then the sectional curvatures are less than or equal to kappa. All right? But we'll only prove one direction, this direction. All right? Is the statement clear?
Yes, sir.
Okay. So the idea will be to use the last proposition that if the angle function is less than or equal to the comparison angle, then the space is cat kappa. So for the angle function, we'll take the Riemannian angle. Okay, so what we want to show is that Riemannian angles are less than or equal to comparison angles. Okay, that's what we'll show. And the proof will use a sort of comparison theorem for Jacobi fields. Okay, so there's less than a minute, so let's stop here and we'll start again in another meeting. Okay, so let's stop this meeting.